Finally, we are in chapter 8. And in today's lecture, we're going to talk about the conservation of energy and the energy balance. Okay, chapter 8. It's about steady-state non-isothermal reactor design. In this chapter, we will focus our attention on heat effects in chemical reactors because most reactions are not carried out isothermally. Be careful of the name, or pay attention, I should say, of the name heat effects. That's a common terminology that we use in chemical engineering when we discuss the energy balance and the need to incorporate the change in temperature and heat transfer and so on. We will derive user-friendly energy balance equations and apply it to the following cases: isothermal operation, adiabatic operation, heat exchange with a surrounding at constant ambient temperature, heat exchange with a surrounding at variable ambient temperature with a co-current flow, and the last one is with a counter current flow. For an adiabatic exothermic reaction carried out in a plug flow reactor. So let's take a plug flow reactor where we have an isothermic reaction carried out and the reactor is run adiabatically. So the question is, how does temperature change with volume? Of course, since the reaction is exothermic, releasing heat, and this heat cannot leave the system, so the temperature will increase, correct? When the temperature increases, how does K change with volume? Well, obviously, the value of K, rate constant, will increase as well because temperature is increasing, right? Okay, couple that with the change in concentration. This will give you a conversion profile, X versus V. Okay, so that means we really need to know how the temperature changes within the reactor because this will affect the rate constant, and since the rate constant is affected, the rate of reaction will be affected and therefore conversion will be affected. So that's the rationale behind why we need to study the energy balance. Okay, again, let's consider an adiabatic exothermic gas phase reaction carried out in a packed bed reactor. Through mole balance, rate law, stoichiometry, and Ergun equation, we derive a differential equation that is dx by dw, which is function of x, conversion, pressure, and temperature, right? Because all of these, x, p, and t, they all appear in the stoichiometry step. And of course, we have Ergun equation because we have pressure drop. So P is function of W. So from an Ergun equation, we derive a dP by dW equation, a differential equation for pressure. And it's also function of X, P, and T, as you know. Right. So what else do we need? What else do we need? Well, we have here three variables, X, P, and T, right? But we have only two equations, two differential equations. So that means we need a third differential equation. We need dt by dw, right? We need dt by dw, which is function of x, t, and theoretically you can say p as well. But let's take x and t. Right. Where do we get this equation from, dt by dw? Yep, by carrying out an energy balance on the reactor. So let's talk about the energy balance. The law of conservation of energy. The law of conservation of energy is an empirical law of physics. So something which have been noticed in almost all the processes. Therefore, they said, oops, then energy is conserved. Okay, so it's an empirical law of physics. What does it state? Well, it states that Energy can neither be created nor destroyed. It can only be transformed from one form to another. So because energy is conserved, that means any quantity which is conserved actually cannot be created nor destroyed, right? So same applies to energy. So energy can neither be created nor destroyed. It can only be transformed from one form to another. Because energy is conserved, the energy balance is written as accumulation equal input minus output. Simple, because I don't have to add the term plus generation because energy cannot be created. I don't have to add the term minus consumption because energy cannot be destroyed. Okay, so again, any conserved quantity, since it cannot be created nor destroyed, the balance is very simple. Accumulation equal input minus output. Tamam? The question now is this equation valid for system involving chemical reactions? What do you think? So this is equation, accumulation equal input minus output. Can I use it in an energy balance for a system which includes a chemical reaction? Yes, I can, because we just said energy is conserved, right? So it cannot be created nor destroyed. So this is the only way you balance it, yeah? So this equation is valid whether the system involves a chemical reaction or not. Okay, so again, accumulation equal input minus output. So we said energy cannot be created, and a lighter tone, instead of created, people say generated. And energy cannot be destroyed. In a lighter tone, people would say it cannot be consumed. Okay, so that's the wording that we use when we write balance. Okay, so energy is conserved, therefore accumulation equal input minus output. For a closed system, how energy can be exchanged with the system? If we have a closed system, we have a closed system, how can we exchange energy? Yani, how can energy comes into the system and how energy can leave the system, so that as a result there would be accumulation? Well, for a closed system, since I cannot exchange mass, the only two ways are through heat and work, right? So for a closed system, the energy balance is therefore written this way. So dE total for a system, the accumulation of the energy within the system, is related to input and output through heat. So here this is input minus output, and also through the exchange through work. So this is the only way. Of course, this is minus W, so you can read it as, here, this guy, you can read it as output minus input, because there is a negative behind it, so it will switch to input minus output. Okay, so this is in the differential form. I can really write it in the integral form and integrate this, and then the accumulation simply written as delta ET system, that's accumulation, equals Q minus W. So let's look at Q, which is heat. So if heat is coming into the system or added, of course it will be positive. If Q is out or removed from the system, the value will be negative. So I don't change the equation. I do not change the equation. I'm talking about the value. The numerical value should be here negative if it's out. For the work, it's opposite. So work out or done by the system is positive. So when I put a positive number here, it becomes negative, right? So because it's leaving the system, And for the work which is coming in, of course, eventually should be a positive, صح? But here, the value will be in negative. So work in or done on the system is negative. So just to explain where this is coming from, well, it's coming from the mechanical engineering concept. That is, if you want to generate a work, you can add heat, add heat, and then the system will do work for you. So it will push this piston up. It will do work. It will do work. So they like doing work. So that's why the work done by the system is positive. So that's something they want. Okay, so but however, when the system does a work, it's losing part of energy, so it should be considered as out. Therefore, they put a negative behind before the work. Okay, and let's see one more thing. Let's see one more thing here. That is the delta. So the delta here, the delta signifies that delta Q and delta W. So we're talking about here, these guys. Delta Q and delta W are not exact differentials of a state function. Okay, so I know that Q and W are not state functions, right? They are path functions. So the derivative of a path function is an inexact derivative. Okay, inexact derivative. And for an inexact derivative, we don't write d, we write delta. And of course, ET system is the total energy of the system. So let's take a couple of examples to clarify the concept of the conservation of energy in reactive system, and that even in reactive system, the energy balance is still written as accumulation equal input minus output, meaning without the generation and consumption terms. Okay, so let's take the first example here. The reaction CO plus half O2 gives you CO2. It's carried out isobarically and isothermally in a piston cylinder reactor at 25 degrees C with 1 mole of CO and half mole of O2. The reaction is assumed to proceed to completion. Okay, as you see, we have 1 mole of reactant goes to, 1.5 mole of reactant goes to 1 mole of product. So that means the total number of moles is decreasing, therefore the volume will decrease as well. That's why you see that the piston has came down after the as the reaction proceeded. Okay, starting from the balance equation for conserved quantities. So we're going to use the balance equation for conserved quantities, that is accumulation equal input minus output. Derive an equation to calculate the amount of heat that must be removed from the reactor for the reaction to proceed at constant temperature. Of course, this reaction is exothermic, it's combustion, and in order to carry out isothermal, you need to remove certain amount of heat. Right, so let's begin then. Accumulation equal input minus output. Accumulation equals delta E total for the system equals Q minus W. Okay, so let's look at delta E of the system. Of course, delta E consists of delta U plus delta kinetic energy plus delta potential energy. So all of these changes that contribute to the change in the energy of system. Tamam? Okay, what does it equal? Of course, equals input minus output through what? It's a closed system, through heat and work. So through heat is Q minus work would be considered as a boundary work, the work that the piston would do on the system, or the boundary that is doing on the system in order to shrink, right? Okay, and that equal integration of P dV. Okay, so do you have any change? Do you have any change in kinetic energy of the system? So is the piston cylinder device, is it changing its speed? No, it's not. Is it changing its position? Well, also not. Actually, it's changing, the center of gravity is changing a little bit. It's getting lower, but this is really negligible. So you can say almost zero. So the only thing remaining is delta U total, and then the integration of P dV. Of course, the pressure inside the system is constant. It's a piston cylinder device. Tamam. P goes outside, the integration of dV will be delta V. So it goes to the other side. We have delta UT plus P delta Vt equals Q. Okay, and of course, you all guys know that this boils down to delta H. Why is that? Because you know that H equals U plus PV, correct? So delta H equals delta U plus delta PV. But of course, here delta U, of course, P is constant, so goes outside the delta. So this guy equals delta H, and all of this for the total of the system. So we have delta H total equals Q. Tamam? Okay, let's define what delta H is. Well, delta H, which is the change in the enthalpy of the system, can be evaluated by looking at the enthalpy at the final state and the enthalpy at the initial state, correct? So if you compare these two, if you subtract H final from H initial, this will give you the change in the enthalpy of the system. So let's see what we have finally. Finally, we have 1 mole of CO2, correct? Okay, so the final is the enthalpy of CO2 at 25 degrees C, because the reaction was carried out at 25 degrees C, correct? Okay, and 1 mole of it, of course. Tamam. And initially, what did we have initially? We had 1 mole of CO at 25, so this is initially, and also we had half mole of oxygen, so plus 0.5 HO2, also evaluated at 25 degrees C, right? Okay, if you multiply the negative inside, you'll get this equation. Do you remember this equation? You know what this is? Yes, this is exactly the delta H reaction at 25 degrees C. So the Q, the amount of heat that needs to be removed, equals the delta H reaction at 25 degrees C, correct? Okay, what does this prove to you? This proves to you that the term delta H reaction is or appears in the energy balance equation, not because I started with accumulation equal input minus output plus generation. No, this is not the case. I know that energy is conserved, therefore I cannot write accumulation equal input minus output plus generation. It's only input minus output, and this is how I proceeded, right? This is how I proceeded. And as a result, I got the delta H reaction. So the delta H reaction actually is part of final minus initial, tamam? Or input minus output if you want to look at it for an open system. So let's answer this question. Does the quantity delta H reaction appears in the energy balance because we started from accumulation equal input minus output plus generation, where generation is delta H reaction? And the answer is no. Actually, this equation is wrong for energy balance. Okay, let's take another example. The same reaction, CO plus half O2 gives you CO2. It's carried out isobarically and adiabatically. in a piston cylinder reactor. Okay, so now I'm maintaining the pressure constant through using the piston cylinder reactor, and not allowing for any heat exchange. Because the reaction is exothermic, as you know that the temperature will increase. The reactor was initially charged with 1 mole of CO and half mole of O2 at a temperature of 25 degrees C. Starting from the balance equation for conserved quantities, accumulation equal input minus output, derive an equation to calculate the temperature at the end of the reaction, assuming that it proceeds to completion. So now we need to derive an equation to calculate the temperature at the end of the reaction. So I'm assuming that it proceeds to completion. So let's start with the balance equation that is written for conserved quantities, because energy is a conserved quantity. So accumulation equal input minus output. Again, this is translated into delta E system, the accumulation of energy E within the system, equals input minus output. And since this is a closed system, the only way to exchange energy with the environment, the only way you can have energy in and energy out, is through heat and work. Okay, so we already know how to write delta E system. Any energy consists of these three components: internal energy, kinetic energy, and potential energy. And then we are saying we're running adiabatically, so Q goes to 0, and we have the boundary work, that is the work related to the expansion and contraction of the system of the boundary. Here is the integration of P dV total, or can carry out the integration. T is constant, goes outside the integration, and then we have here P delta V, and we have from the left hand side delta U. So that's how we write it. And of course we know that this is written as delta HT equals to 0, or the enthalpy of the final state minus the enthalpy of the initial state should equal to 0. So let's look at the system finally, and let's look at the system initially. So finally, the system consists of only CO2, 1 mole of CO2, correct? At a temperature of T, because now the temperature has raised, right? Because the reaction when preceded, it released heat because the reaction is exothermic. This heat could not leave the system because the reactor was operated adiabatically, so it stayed inside, and now we have energy, extra energy inside. It's going to be absorbed by the molecules, right? Their movement will increase, their speed of movement will increase, and this will be translated in higher temperature. Okay, and initially what did we have? We had 1 mole of CO at 25 and half mole of oxygen also at 25. Okay, tamam. So how do we express this term? Well, simple. So this term can be found from the enthalpy of CO2 at 25 degrees C plus the increase in enthalpy due to the increase in temperature, which is found through the integration of Cp dt, evaluated from 25 degrees C to the T of the system. And then here we just multiply the negative inside the bracket. So you have negative HCO at 25 degrees C, negative 0.5 HO2 at 25 degrees C as well. Okay, let's assume we have a constant Cp or an average Cp. So we take it outside the integration, and then we have integration of dt is t evaluated from 25 to 20. We get this term. Okay, and let's take this to the other side. Let's take this to the other side. Okay, so what do we have now? When we take this to the other side, we can rearrange it this way. So we take this to the other side, we take these to the other side as well, and rearranged it, and we write it this way: minus HCO2 at 25 minus HCO at 25 degrees C again, minus 0.5 at H multiplied by HO2 at 25 as well. So what do we have here? What is this? Yep, that is exactly delta H reaction, and then you have a negative here, so it's negative delta H reaction at 25 degrees C. Again, where did this term come from? Did it come from the fact, no, did it come, I shouldn't say a fact, did it come from the term plus generation when I did the balance here? Of course not. It cannot be, because I do not have plus generation there, because the energy is a conserved quantity. So because energy is conserved, the energy released from the reaction heated the gas inside the reactor, as it could not leave the system. So now I hope that you fully agree with me when we say that this balance is used to balance energy whether we have chemical reaction or not. That is because energy is conserved. In other words, I'm saying that I hope now you believe that this term, delta H reaction, is not really coming from accumulation equal input minus output plus generation, but it's part from the input minus output. And again, this is because energy is balanced and energy is conserved, and the only way it can be balanced through writing accumulation equal input minus output. Okay, the first law of thermodynamics. So we said for a closed system, the energy balance is written the way shown here. For an open system, how energy can be exchanged with the system? How can we have energy accumulated within the system? Energy can be accumulated through the system by input minus output. So what are the means for input and output? Well, you know that one of them is heat, the other one is work, the third one is the energy exchanged due to mass exchange. So for an open system, the energy balance for the case of one species entering and leaving the system can be written as here: accumulation equals input minus output through heat minus output minus input through work, and plus input minus output through mass, the mass which is coming in and leaving the system. And you can see that we are multiplying the mass coming in with energy and the mass going out with energy, except that as a chemical engineer, I prefer to work with number of moles instead of mass. That's why we have Fn times the En minus F out times E out. Okay, so again, this is my system, which is a reactor in this case, and we have exchange of heat, exchange of work, and then we have mass coming in with its associated energy and mass leaving out with its associated energy. Tamam? So there we go. Accumulation within the system equals the rate of flow of heat to the system or from the system, and minus work, and then we have the two terms related to mass exchange. طيب, the unsteady state energy balance for an open system that has n species. So we don't have only one species, no, we have n number of species, each entering and leaving the system at their respective molar flow rate, and energy is written this way. So please note that we have added the summation sign here and there. Type. In the next lecture, we will discuss each of the terms in the above equation, actually in the next segment. Okay, so we'll see you then.